Good morning, sir. My name is CHUAN, and today I would like to give a brief introduction to the experiments I conducted this semester. I have carried out 5 experiments, each focusing on different areas of physics. The first experiment was in optics, where we explored the phenomenon of Newton's rings by observing the interference pattern created by a thin film of air between a plano-convex lens and a flat glass plate. This helped us measure the wavelength of light and understand the principles of interference. In the second experiment, we delved into mechanics by analyzing tension and kinetic friction, gaining insights into the forces acting on objects in motion and at rest. We measured the tension in a string and the frictional force between two surfaces to understand the factors that affect motion. In the third experiment, we focus on direct current, DC, circuits, measuring the internal resistance of a power source and assessing the precision of a galvanometer. This taught us about Ohm's law, the behavior of electrical components in a circuit, and the importance of accurate measurements. The fourth experiment involved alternating current, AC, circuits, where we determined the impedance of an inductor and a capacitor using an oscilloscope. By analyzing voltage and current waveforms, we calculated the reactance and impedance of these components, highlighting their frequency-dependent behavior. Lastly, in the fifth experiment, we investigated the refraction of light, measuring angles of incidence and refraction to apply Snell's law and understand light propagation through different materials. For the first experiment, which is Optics 1, Newton's ring, the objective is to measure the wavelength of sodium light using the method of Newton's rings and to become familiar with using a vernier microscope. In this experiment, we utilized the physical property of light interference to determine the wavelength, lambda, of a light source. The experimental setup began with cleaning, result and error analysis. After obtaining the results from the experiment, the first step is to tabulate the measurements into a table for clarity and organization. Next, we will plot the straight line graph of R n square versus n. The error analysis involves calculating the gradient and y-intercept using the least squares method. To ensure accuracy, we must also calculate the uncertainty for both the gradient and the y-intercept. From the equation, R n square equals n R lambda, where R n square is the square of the radius of the nth ring, n is the ring number, R is the radius of curvature of the lens, lambda is the wavelength of the light used. We know that the gradient, m, of the graph is equal to R lambda. Our goal is to find lambda, the radius of curvature of the lens, R, is measured using a spherometer, and its uncertainty is also calculated. From the graph, we obtain m equals R lambda equals 0.0004 plus or minus 0.0002 centimeters squared. Using the spherometer, we determine R equal to 10.3 plus minus 0.3 centimeter. Thus, by dividing them, we get lambda equal to 388 plus minus 200 nanometers. Discussion. What would be the effects on your graph if I thus was preventing perfect contact between the lens and glass block? 2. The lens and glass block were pressed so tightly together that the lens became flattened around the point of contact. 3. The surface of the lens was not accurately spherical, thus preventing perfect contact between the lens and glass block. If dust particles are present between the lens and the glass block, they will act as spacers, creating an uneven gap. This would result in inaccurate measurements of the radii of the interference rings because the air gap would not be uniform. Consequently, the plot of Rn square versus n might show irregularities or deviations from the expected linear relationship, making it harder to determine an accurate gradient. 2. Lens and glass block pressed too tightly. Flattening the lens. Pressing the lens too tightly against the glass block could cause deformation, making the lens surface flatter around the point of contact. This would decrease the curvature radius R, causing the interference fringes to be less evenly spaced. The result would be a different slope in the graph of Rn square versus n, potentially leading to a lower measured value of R and inaccurate results for R lambda. 3. Surface of the lens not accurately spherical. If the lens surface is not a perfect sphere, the spacing between the interference rings will not follow the expected pattern. This would cause deviations from a linear plot in the graph of Rn square versus n, leading to errors in determining the correct radius of curvature R. The gradient might not be constant, indicating that the lens does not have a uniform curvature. Comparison of sodium light and neon light with accepted values. The accepted wavelength for sodium light is around 589 nanometers, while the accepted wavelengths for neon light range from about 400 nanometers, violet, to 750 nanometers, red. Given our calculated lambda is 388.3 nanometers, with an uncertainty of 200 nanometers, our result overlaps with the accepted values for both sodium and neon light sources within the uncertainty range. However, to achieve more precise results, reducing experimental errors and uncertainties is crucial. Should there be any significant difference in the result for using the sodium or neon light source when conducting a Newton's ring experiment to measure the wavelength of light using sodium or neon light sources can yield different results due to their distinct wavelengths. Sodium light, which typically has a wavelength around 589 nanometers, produces clear and evenly spaced rings owing to its single, well-defined wavelength. This makes sodium light particularly useful for precision measurements and obtaining distinguishable ring patterns. On the other hand, neon light, which has multiple wavelengths, may produce overlapping patterns. This complexity can make the rings less distinct and harder to measure accurately. Therefore, while both light sources can be used, sodium light is generally preferred for its clarity and ease of interpretation, leading to more precise experimental results. The second experiment I conducted is Mechanic 1, tension and kinetic friction. The objectives of this experiment were twofold. Firstly, I aimed to understand the relationship between tension, angle of the segment, and the coefficient of friction. Secondly, I sought to determine the value of the coefficient of friction by measuring the tension for two specific ranges of angles, 0 degrees less than or equal to theta less than or equal to 360 degrees and 360 degrees less than or equal to theta less than or equal to 720 degrees. For the experiment, a mass of 1.5 kilograms, consisting of a 0.5 kilograms and 1 kilogram load stacked together, was attached to a string, assumed to be massless, with a spring balance on the other end. The string was positioned at different angles in increments of 45 degrees, ranging from 0 degrees to 360 degrees. For each angle, the load was allowed to fall at a uniform velocity, and the tension in the string was measured using the spring balance. These measurements were repeated 3 times at each angle to ensure accuracy, and the average tension was calculated and recorded. A second part of the experiment was then conducted, extending the angles from 360 degrees to 720 degrees using the same procedure. All data was documented in a table for further analysis, providing a comprehensive view of the relationship between the angle and the tension in the string. From the graph of ln t on the y-axis against theta on the x-axis, the coefficient of kinetic friction was determined. For the range 0 degrees less than or equal to theta less than or equal to 360 degrees, the coefficient of kinetic friction was found to be 0.22 plus or minus 0.08. For the range 360 degrees less than or equal to theta less than or equal to 720 degrees, the coefficient of kinetic friction was found to be 0.17 plus or minus 0.06. Discussion. For the experiment, two ranges of angles were analyzed: 0 degree less than or equal to theta less than or equal to 360 degree and 360 degree less than or equal to theta less than or equal to 720 degree. The data from these ranges can be plotted on graphs of tension T against angle theta. In both cases, the tension T decreases exponentially as the angle theta increases, as suggested by the theoretical equation. T equals T naught e power of negative mu theta. The key difference between the two conditions is that in the first scenario, the string is wrapped around the rod for only one complete revolution, 360 degrees, whereas in the second scenario, the string is wrapped twice, 720 degrees. This implies that the tension decreases more rapidly in the second case due to the increased number of wraps, which enhances the frictional effect. The parameters T0, initial tension, and mu, coefficient of friction, may differ slightly between the two conditions, which are 0.22 plus or minus 0.08 for the first scenario and 0.17 plus or minus 0.06 for the second scenario. If the string properties and surface interactions are consistent, mu should theoretically remain the same. However, any deviation in the experimental setup could lead to a slight change. Typically, the values of mu should be consistent across experiments if the same initial tension is applied, but the effective tension experienced after 720 degrees would be lower due to cumulative frictional effects. Another way to determine the coefficient of kinetic friction for a string is to measure the force required to move the string over a surface at a constant velocity. Set up the experiment with a spring balance, string, surface, like a table, weights to apply a known normal force, and a pulley, if necessary. Attach one end of the string to the spring balance and lay the string over the surface, connecting it to a weight if using a pulley system. Place known weights on the string to create a normal force against the surface. Pull the string horizontally with the spring balance, ensuring it moves at a constant velocity, and record the reading from the spring balance, which represents the kinetic friction force. Calculate the coefficient of kinetic friction, mu, using the formula mu equals F K over N, where Fk is the kinetic friction force and N is the normal force. Consider the uncertainties in the measurements of the spring balance and weights and propagate these uncertainties to determine the overall uncertainty in mu. In the experiment, to determine the coefficient of kinetic friction for a string, several sources of error can affect the accuracy of the results. Common sources of error include measurement errors, e.g., inaccurate spring balance readings due to parallax or calibration issues, variations in the weights used to create the normal force, surface irregularities, e.g., uneven, rough surfaces, environmental factors, e.g., temperature fluctuations, air currents, vibrations, string characteristics, e.g., inhomogeneities in thickness or stiffness, and human errors, e.g., inconsistent pulling force, recording errors. To mitigate these errors, several precautionary steps can be taken. Regularly calibrate the spring balance, use precisely measured and standardized weights, ensure the surface is clean, flat, and uniform, conduct the experiment in a stable, controlled environment, use high-quality string with uniform characteristics, and develop a consistent technique for pulling the string at a constant velocity. Taking multiple readings for each measurement and averaging the results can further reduce errors. By addressing these potential sources of error and following these precautionary steps, the accuracy and reliability of the experiment to determine the coefficient of kinetic friction for a string can be significantly improved. The third experiment I conducted is titled Direct Current 1, Measuring Internal Resistance and the Precision of a Galvanometer. The objectives of this experiment are comprehensive and aim to deepen the understanding of various aspects related to galvanometers and resistance measurements. The first objective is to determine the internal resistance of a galvanometer, which is covered in part of impact on measurements, as detailed in Part B. Sensitivity is a vital parameter that influences how accurately the current can be measured based on the deflection readings of the galvanometer. The third objective is to measure the resistance of an unknown resistor using various methods, which is addressed in Part C. Employing different measurement techniques helps in verifying the accuracy and reliability of the results obtained. The fourth objective is to examine the effect of internal resistance in voltmeters and ammeters on the accuracy of resistance measurements for an unknown resistor, as explored in Part D. Understanding how internal resistance influences measurement accuracy is essential for refining experimental methods and improving precision. The fifth and final objective is to compare the effectiveness of different techniques in determining the resistance of an unknown resistor. This comparative analysis allows for the identification of the most accurate and reliable method, thereby enhancing the overall quality of the experimental results. Result and error analysis. For Part A, which involved measuring the internal resistance in a galvanometer, the average value of the internal resistance was found to be G equals 1391 plus or minus 2 ohm. In Part B, the experiment focused on determining the galvanometer sensitivity, resulting in an average sensitivity value of 1.42 plus or minus 0.01 times 10 to the power of minus 6 ampere. Parts C and D of the experiment utilized two different methods to determine the resistance value. In Method 1, readings of the maximum deflection of the voltmeter and ammeter were recorded, whereas in Method 2, 10 sets of different voltmeter and ammeter readings were taken by varying the rheostat. For Part C, where the voltmeter was in parallel with the resistor and ammeter, the resistance value obtained using Method 1 was R equals 4.7 plus or minus 0.7 ohm, and using Method 2, the resistance value was R equals 4.60 plus or minus 0.07 ohm. In Part D, with the voltmeter in parallel to the resistor only, the resistance value determined using Method 1 was R equals 4.4 plus or minus 0.6 ohm, while Method 2 yielded a resistance value of R equals 4.3 plus or minus 0.1 ohm. These results highlight the variations in resistance values obtained through different measurement methods, as well as the overall precision and accuracy of the experimental procedures. In part A of the experiment, we measured the internal resistance in a galvanometer. The internal resistance, Rg, was determined to be very high, specifically Rg equals 1391 plus or minus 2 ohm. This high internal resistance makes the galvanometer suitable for measuring only small currents. Such resistance can affect the accuracy of the experiment, emphasizing the importance of determining the internal resistance of electrical devices before usage. Ideally, the internal resistance of a galvanometer should be small, typically ranging from a few ohms to a few tens of ohms. A high internal resistance, like the one determined in this experiment, can significantly impact the overall resistance of the circuit, thereby affecting the accuracy of current measurements and limiting the ability to measure larger currents accurately. In part B, we determined the sensitivity of the galvanometer. Different galvanometers have varying sensitivity levels, which determine how accurately we can measure current based on deflection readings. The average sensitivity obtained in this experiment is 1.42 plus or minus 0.01 times 10 to the power of minus 6 ampere. This means that to deflect 1 unit on the galvanometer scale, 1.42 microampere of current is needed. A galvanometer with higher sensitivity, such as the one used in this experiment, provides more accurate readings and allows for the detection of smaller currents with greater precision. High sensitivity is crucial for precise measurements, especially in applications requiring the detection of very small currents. In part C, we analyzed the voltmeter in parallel with the resistor and ammeter. The error percentage of R from method 2 was found to be higher compared to method 1. Method 2, which involves averaging values, is typically expected to lead to more accurate measurements. However, several factors could explain the higher error percentage. Method 2 might be more sensitive to systematic errors or anomalies in the data, and averaging could amplify these issues rather than mitigate them. Additionally, specific conditions and procedures in Method 2 might introduce additional sources of error, such as complex calculations or additional measurements, which could accumulate inaccuracies. Rounding off values during calculations might also impact the results. Method 1, involving only a single measurement, had fewer opportunities for errors compared to Method 2. Despite the higher error percentages from Method 2, careful analysis and refinement of the experimental procedures, along with rigorous quality control, could reduce these errors and achieve more consistent and reliable results. For Part D, we examined the voltmeter in parallel to the resistor only. The percentage error between apparent resistance and actual resistance, as well as the error percentage of R from Method 2, was lower compared to Method 1. These results were expected, as Method 2 involved averaging values, typically leading to more precise measurements. Thank you for watching. I hope you enjoyed it.